This is a simple Atwood machine. An 85-kilogram man lowers himself to the ground from the height of 10 meters by holding onto a rope that runs over a frictionless pulley to a 65-kilogram sandbag. With what speed does the man reach the ground if he started from rest? In this situation, we can start by drawing a picture to better understand what's going on. There is the ceiling, and there's a pulley, and the rope is going to a man. For simplicity's sake, since we're going to represent him as a point mass in a free body diagram, we'll say that this is our person right here. On the other end of the rope, there is a sandbag. And so we have, this is M2, which is 65 kilograms for the sandbag. This is M1, which is the man, and that is 85 kilograms. We can realize, too, in this case, you'll have mg acting on both objects. You'll have an m2g and an m1g. We'll also have tensions acting on each object, and those tensions are the same amount because the string itself will spread the tension out through the entire string so that it's an equal amount everywhere. And finally, we know that we're told that the man lowers himself to the ground. So we know that the velocity of the man has to be downwards, the acceleration has to be downwards, and then as a part of our acceleration constraints, if the man goes downward, which makes sense because he's heavier, he should go down, the block will have to go upwards over the pulley. So we can draw a free body diagram for each object. We start by drawing the free body diagram for the man. We have gravity pulling him downwards. We have tension pulling him upwards, and they shouldn't be equal because he is actually accelerating downwards. This is for the man, we're calling M1. For the sandbag, which we're calling M2, we have a weight, a force of gravity downwards as well, and we have a tension that is upwards. And the two tensions should be equal because it's the same tension being transmitted via the rope. So we can now write our Newton's second law equations. In each case, we're only moving up and down. There's only a y direction. In the case of the man, our forces are: we have a tension that's upward, we have a mass of the man that's downwards, and our acceleration is downwards. We said that acceleration is downward for the man, it's upward for the block, and so if we want mass times acceleration, what we're going to do there is to negate that, so that here we have the magnitude of the acceleration. That's the direction of the acceleration. Because they are constrained to move together, their value of the acceleration has to be the same, but the direction doesn't have to be the same, so that's why we want to decouple the magnitude and the direction. For the sandbag, we'll do the same thing. We have gravity upwards, we have the weight of the object downwards, and that will equal mass times acceleration, and it is accelerating upward, so that's a positive amount. We can also see the tension has to be greater than the mass of the sandbag to pull it up. The tension here is less than the weight of the man, that's why he's falling downwards, and that's why it should equal a negative value. So here we want to find, we have looked at the forces acting. What we're actually interested in is at what speed. So we want to know how fast he is hitting the ground. So what that's telling us is that even though all we know is about the masses which give us forces, we actually want to know the speed. So that means we want to know the acceleration from Newton's law. We'll use the acceleration to find the speed. So here, what we don't know the tension in the rope, we don't know the acceleration of this man and sandbag system. But we don't care about the tension, we only care about the acceleration. So what we're going to do is multiply through by a negative here. That will negate, and that'll make positive, and that'll make positive our terms. Because now what we're going to do is add these two equations. We're going to add these two equations. If this equals that, and this equals that, then this plus this must equal that plus that. And when we add, we have a negative tension and a positive tension. Those will just cancel out completely. We have that. We can simplify. What we see here is this is the net external force on the system. The net external force on the system is the gravity pulling on each object, even though the gravity is pulling more on one object and it's pulling against the other object. This is the total external force. The tension doesn't count as an external force, it's an internal force, and thus it is not making our object accelerate at all. This is the external force, is making the entire mass of the entire system, which consists of both objects, accelerate together. From here, we can say that the acceleration will be g So our acceleration will be approximately 1.31. In fact, it will be 2/15 of g of gravity. So if we know how fast he's accelerating downwards, we know that this is a constant acceleration, this becomes a kinematic problem. We know that the acceleration is 1.31. If it's downwards, we'll call that a negative. We know that he starts from a height of 10 meters and he hits the ground later, so that means that his change in position is a negative 10 meters. And we know that his initial velocity is 0 meters per second. We want to know what his final velocity is. We're told that he started from rest, so that's his initial velocity. We're asked with what speed does he hit the ground. That's his final velocity. We'll pick the appropriate constant acceleration equation. This term is 0. These are both negative, a negative acceleration and a negative displacement, which cancel out and end up being positive. And his velocity ends up being 5.1 meters per second. That velocity should be downwards, it should be a negative amount, but when it says the speed, we don't worry about velocity being a factor, we just care about the amount. And so we can say the speed, or v without the vector notation, will be just 5.1 meters per second.